Welcome to the webinar. The webinar will begin shortly. Welcome to the webinar. The webinar will begin shortly. Welcome to the webinar. The webinar will begin shortly. Welcome to the webinar. The webinar will begin shortly. Welcome to the webinar. The webinar will begin shortly. Welcome to the webinar. The webinar will begin shortly. Welcome to the webinar. The webinar will begin shortly. Hello everyone and welcome to the webinar. My name is Bob Wentz and I shall be the moderator for the webinar. The webinar is entitled Overcoming Water Industry Stringent Wastewater Phosphorus Standards, and it will be presented by Paul Barter of Jacopa. There will be a short time for questions and answers at the end of the presentation, but please note the presenter's details, which will be shown during the Q&A session, should you wish to contact them for further information. And also, during the webinar, could you please post your questions using the Q&A button in Teams. At the end of the webinar, I will put up a slide showing the following webinars after this session, so please do take a note of them. Well, thanks very much indeed, and I'd now like to hand over to you, Paul.
Good afternoon, everybody. I hope you're enjoying your day. I'll just share my screen if I may. Hopefully that's all popping up nicely. I'll now switch to my presenter's view, so I'll get going. So I'm Paul Barter, I'm the process manager for Jacopa, looking at lots of the tertiary technologies. Jacopa about 18 months, 2 years ago, took on the license for the Nordic Water range of products. Mainly, well, the Dyna sand is probably the best known single product from their range. I've been working with Nordic Water for a number of years, so I moved across when the license went across to Jacopa to continue my work with them. So I'm going to be talking about ultra low P technologies today. I'll be looking at basics of P removal, which I'm sure everybody here will know by now. I'll be talking about two technologies in particular, the Dyna sand and the Dynacloth, how they work, and I will go through some case studies. So hopefully it'll be of interest to everybody. So why remove phosphorus? Well, I think everybody knows that the Water Framework Directive tells us it's probably the single biggest failure for our water courses and our freshwater sources in the UK, and if we can reduce phosphorus load to them, we can get some of these courses back up to a good status. So this is all sort of set out by the Environment Agency and the EU Water Framework Directive. So how do we remove phosphorus? There's a few ways of doing it. You can do it biologically. Phosphorus is part of a cellular organism structure, and we can encourage phosphorus to be taken up by biomass within the wastewater treatment works. By giving it the right conditions, you can encourage certain growth of certain bacteria which like phosphorus, and that's great. That's a really good way to remove phosphorus. You get it out in the biology, you're not having to add anything else in chemical wise, and you might even be able to release that phosphorus again. Phosphorus is a finite resource, so if we can get it back from wherever we take it out from in the water, we can then use it back in its original applications, fertilizers and whatever. Unfortunately, to get to the very low levels that we need to meet the directive, we're talking chemical phosphorus removal. The most common of which are, well, aluminium or iron, ferrous or ferric iron, or you can use calcium. So the case studies are based on aluminium or iron dosing into filters. By far the most common I've come across in the UK is iron dosing, normally ferric sulfate or ferric chloride. Ferric sulfate seems to be the best cost advantage at the moment, but that can change as prices for these products change. So dosing points, we've got a number of choices. We can dose as a pre-precipitation stage, normally in front of the primary tanks. We can do a co-precipitation stage, so immediately it goes into the secondary, or as it goes into the settlement stage of a secondary treatment process, or we can dose into the tertiary stage of post-precipitation. Normally, to get to these very low levels, we're probably using a sort of two dosing points, maybe a pre-precipitation with a post-precipitation seems to be probably the most common. Pre-precipitation taking out the bulk of the load, and the post-precipitation allowing you to reach the very low levels that we require. So ultra low technologies that we're talking about, Dyna sand. Dynasand may be considered a bit old hat now. It's been around since 1979 when it was first invented by Nordic Water. First plants in the UK were in the 80s, and there's lots of plants in the UK successfully using it. But the long history's a big plus point as well. We've got you can see how it's been working. There's lots of case studies, and we have been using it to reach very low P consents for an extended period of time. So I'll go through a couple of case studies showing what sort of levels can be achieved. Then I'll talk about the Dynacloth, which is a pile cloth media filter. We've got quite a significant range of experience of that, about 10 years, and again reaching very low P consents, 0.1 to 0.2 milligrams per litre, the sort of very low numbers we're looking at for the UK. Most of the experience for the Dynacloth was built up by the original Dyna, which is a South Korean company. Now that technology has been incorporated into the Nordic range and is now being manufactured in Sweden. So first of all, Dynasand. Hopefully lots of you come across how they work. I'll go through it briefly in case you haven't. Water is fed into the top of the unit and piped down through the central column, radiated out by the water distributor over the entire surface area of the bed. The water then flows up through the sand bed and the fine particulates are captured within the sand bed. It then discharges over the overflow wheel and away as the final effluent. At the same time, you apply a small amount of air to the bottom of the airlift pump. That raises dirty water and sand from the bottom of the unit to the sand washing section. At the top, when the air is released, the heavy sand particles fall down through the washer, while a small proportion of the flow that's already been treated flows up through the washer, capturing those fine materials, the suspended solids and the chemically bound phosphorus into the dirty wash water. So going on to the case studies, Vaxxo in Sweden. So Vaxxo is a lakeside community in Sweden. The lake nearby was suffering from high phosphorus levels. They looked at what sort of levels the lake could handle naturally in terms of phosphorus, and they decided that they needed to get the phosphorus discharge from Vaxxo, which is by far the biggest source of phosphorus into the lake, down to 0.2 milligrams per litre annual average. And this was a little bit before we'd done anything over here in any great detail. So this was in 1996. It's a big plant, 80,000 population equivalent, and about 3,000 meters cube per hour as a maximum flow. So a big plant by even UK standards. But it has been operating an awful long time. So it's a big plant, so it requires a lot of filters. In this case, we're using concrete-based Dynasands, where you have a number of Dynasand internals in a concrete basin. We have 6 basins with 10 filters in each in a 2x5 format. That gives us a total filtration of 300 meters squared, and if you remember from the previous slide, the flow rate is 3,000 meters cube per hour, so that gives you a hydraulic loading rate of 10 meters per hour at maximum flow. In this particular case, we were looking for suspended solids of less than 8 milligrams, BOD of less than 10, and a total P of less than 0.2. So tough, not ever so tough, but pretty tough standards, and something quite interesting to go for. As I said, the big advantage of this is it was built in 1996, and therefore we have lots of data on it. So the first one says total suspended solids. You can see coming onto the filter plant, we've got a very good level. So this is from the final settlement tanks, round about 8 to sort of 15 milligrams per litre coming onto the filters. And if you remember, the consent was 8 we're after, and you can see we're consistently meeting that year in, year out for the time scale on there, which is what, nearly 20 years. So you can see it's achieving its TSS objective. But from this presentation, we're really talking about total P as being our primary focus. So this is the same data for for total P in and out. Again, it was achieving good results anyway. It had a pre-precipitation dose into the primary tanks to take out the bulk load, and it was achieving, I would say, what, about half a milligram per litre annual average total P in. But consistently out, you can see it's working at 0.1 milligrams average, annual average total P consistently. In fact, they reduced the iron dose on these filters to save chemical costs, because it was more than meeting the objectives they set out. Obviously, this is yearly data. It's perhaps nice to see what it looks like on a month by month basis. So this is the monthly data. You can see that the total P in does vary, as you would expect it to, month by month, but out is consistently at a very low level. This is a different plant. I'm not going to try and pretend to try and be able to pronounce that correctly, but you can see again very similar results. Total P in 0.6 to 0.8, consistently out at 0.1. And this is a Finnish plant. This is a small pilot plant used to size the works. And again, you can see the total P in. Well, it can be quite low. It's less than 0.2 on occasions, but it peaks at 1.1, and it's consistently coming out at about 0.1 milligrams per litre again. So very good results, and that did lead to a full-scale plant being installed later. Well, that's obviously in Sweden, Finland, Nordic countries. So now let's have a case study closer to home. Watton in Anglian Water. Dinah saying weren't quite aware of what we could do with both ammonia removal and total P removal in a single stage. Therefore, we were looking to try and get as much out as possible, bearing in mind that you require a little bit of phosphorus to actually meet the ammonia consent. Obviously, because nitrification requires a little bit of phosphorus for it to work. So we weren't quite sure if we chemically bound phosphorus, if we would still be able to get the ammonia removal. Now, this was part of the CIP2 trials. It was a bit misreported in the CIP2 documents as Dynasand, where it isn't. It's Dynasand oxy, and that's obviously a different process, trying to achieve both of these in one stage. On the trial, it achieves a total P annual average of 0.29 milligrams per litre. It probably could have done a little lower than that if there wasn't some issues with the upfront dosing, probably about 0.25 to 0.2 milligrams per litre. It also achieves ammonia of less than 2 milligrams per litre on a 95 percentile basis. So very interesting. Have a look at it in the CIP2, but do bear in mind it wasn't Dynasand, it was Dynasand oxy, and it's a little bit disgruntled for me that it was misreported. Going on to the Dynacloth, hopefully you've had experience of cloth filters, you know the idea here. So this is an outside to inside filtration process. The effluent, which is chemically dosed again, normally with ferric or aluminium, mainly ferric in the UK, and perhaps polyelectrolyte too, is fed onto the inlet of the into the outside of the tank. It flows through the discs, pile cloth media, capturing the particulates, and then into the central treated drum of outlet treated water that then flows on to the next stage. Obviously, that's going to blind the cloth over a period of time as the solids build up, and therefore we cleanse that by using a suction pump on a section that sucks, holds close to the disc and sucks the pile cloth into straight lines and pulls the captured material out. So we can clean 3 discs at a time, then rotate through the disc up to a 32 disc filter. So looking at the internals of the unit, so this is for a concrete installation. You can see on this particular one it's a 21 disc unit, so it has 7 backwash pumps and 2 desludge pumps to capture the material that falls into the bottom of the outside tank. Water flows from the outside to the inside and then discharges through the main central drum. We can see here is the main holding bearing on the inlet side. You can't see the discharge side on these particular photographs. I've got a sort of cut through drawing just to give you a better idea. This can obviously sit in a concrete tank or into a stainless steel tank. There's one pump for every 3 discs and 1 or 2 desludge pumps depending on the size of the unit. Go through some of the key features of this. So there's a maintenance platform, so you can get better access to the discs to take the discs off if they do require cleaning. It's very easy to do on these filters. I'll go through that in a bit more detail in a minute. You've also got a maintenance platform to work on the backwash pumps located to the size. There's also the drive unit. We use a stainless steel chain on an oversized cog to drive the unit. That minimizes the amount of force required to rotate the drum and gives it a long service life. These are the suction shoes. That's probably the word I was trying to think of earlier that didn't come to mind, which will clean the cloth. There is the cloth has to line a particular way, so it's depending on whether it's inside or an outside cloth. They're slightly different colours, which make sure that the pile lies in the correct fashion to work in the particular application and allow for the direction of rotation of the shoe. And obviously 3 of those acting at one time to clean the discs. These are the filter panels. Our filter panels are very easy to remove, so you've got good access to clean the inside of them if anything builds up on the inside. You're just removing the screws on the outside, taking that guard off that you can see, and then you can slide the panels out. So both panels either side of this come out very easily. I think this goes through it in a little bit more detail. So you've just got it's very easy to remove all the panels and then backwash clean them with a power hose if that's required. It's not a regular occurrence, but it's certainly nice to be able to clean these very easily. I've got a maintenance schedule. I won't go through that in detail. If you want more details on this, please do get in contact. But you can see it's not overly torturous route to maintain these. You're looking at the drivetrain and the filter cloth on a quarterly basis, and a quick visual inspection on a weekly basis, and then the normal sort of things regarding seals and bearings on an annual basis. What I consider Jacopa's big selling points in this is obviously continuous operation. Our difference is obviously the strong drive chain, the stainless steel drive chain, and the large driving cog, minimizing the torque forces. We have a range of sizes starting at 1 meter and going to 3 meter diameters, depending on the particular situation. Most are the 2.1 meter diameter, which is a 5 square meter filtration area for most applications. Seems to be where the market has settled. We've got a long track record, over 10 years experience with these, and over 500 filters installed. So just to give you an idea, these are some of the filter installations. These ones are all in the Far East, mainly in South Korea, and these are on tertiary removal, P removal, and even some CSO type applications. We have a number of pilot units, so if any of you are interested to run a small pilot trial to see what a Dynacloth can do for you, we'll be more than happy to have a look at it. 3 very small units and then a couple of slightly larger ones. The Evo one is for high solids application. It sort of incorporates both the disc filter and the cloth filter technology and has 2 systems for washing the pile cloth. Some of the results from that: this is a pilot study for in Seoul City in South Korea. You can see here a typical influent characteristic, I suppose. 9.2, good solid 6, total phosphorus 1.1, not too far from what you would expect to see over here. And then you can perhaps on the effluent, you can see very, very low solids and corresponding lowering of BOD, and a phosphorus target 0.11 milligrams per litre, so that's 90% removal. This is another plant showing again over 95% removal of total P on a very, very large flow rate plant. And finally, this is a system using PAC and polymer dosing, and again achieving a total P of less than 0.14 milligrams per litre and a removal rate of over 90%. So I think that gives you a good idea of what these are capable of. We're getting a number of installations going into Europe, into Scandinavia at the moment, and hope to get our first into the UK very, very soon. And well, I'm about 5 minutes ahead of schedule, which is all good. It gives you plenty of time to decide where to go next. And I would like to invite some questions if there are any.
Yeah, thanks very much indeed for that, Paul. Thank you. Can I invite everybody, please, who hasn't done so yet, to post your questions up in the Q&A area. But I have one here for you, Paul. It's anonymous, but the question is, how many installs of the pile cloth filter do you have in the UK, please?
I think probably I'll answer that at the very end. We are hoping to get our first one very soon and hope to get a few others in short order behind that. We've got, as I said, I've got a number in Europe already.
Okay, thanks very much indeed. Next question is, what sort of coagulation and flocculation is required on both the Dyna sand and Dynacloth? Okay,
so for the Dyna sand, you would use a high valency metal, ferric, chloride ferric sulfate, and you would dose it immediately prior to the sand filters, normally via a static mixer on the inlet feed line. There is no need for any flocculation tanks, holding tanks, or anything like that to build flock size. The actual flocculation occurs within the filter itself, and then that removes, grabs and holds of the solids and removes the solids as well. So there's no additional tankage required if you're going down that route. For the Dynacloth, you have to build the flock size first. There's no time or opportunity within the Dynacloth itself to do that. So you're probably looking at a 5 to 7 minute flocculation coagulation time upstream of the units, where you would dose ferric and polyelectrolyte as well to increase the flock size to one suitable for removal by the pile cloth.
Okay, thanks for that, Paul. The next question I have for you is, what is the typical life of the pile cloth?
We expect the life to be 5 to 10 years. They've got ones in South Korea that have been in operation for more than 10 years already.
Okay, fine, thank you. And the last question I have for you at the moment is, how much backwash does the Dynacloth generate?
Well, depends on the solids load. Obviously, the more solids, the more times you're going to have to backwash it. Typically, we see 2 to 3% of the influent flow required as a backwash water volume. Okay, fine. Thanks very much indeed. Okay, well, thank you very much indeed for that, Paul. Let me just go back to my presentation for a wind up few comments. Okay, that's it. Well, again, thank you very much indeed, Paul, for that presentation. That was most interesting. Thank you. And thank you all to all of you who have attended this session. At the end of this webinar, I'm going to put up a slide showing the next 2 sessions. So if you're interested in those, it'd be really great to see you attending them. But other than that, thanks again, everyone, and goodbye for now. Thank you.